All right, my friends, section 11.3 is called the tangent line problem. Bet you didn't know you had a tangent line problem. But not only do you, but you, assuming that you're going to continue with math for a while, you're going to have a lot of tangent line problems. So let's draw a picture to make sure that you kind of know what we're looking for. So, oh, that's a rough start. Okay, okay, I had a straight edge around here somewhere. I swear I did. Here it is. Okay, let's just do this. All right, so let's say you've got a graph. You know, little XY plane here. And you have a graph of a given function. We shall call this function f. So here's, sorry, I don't know why that bothers me so much. Okay, so here's what we're looking for. We're looking for a way to basically take any point, say A, at any point where, say, x equals some a value, and to be able to figure out what's the slope of the tangent line to the curve there. So just to give you an idea as to what a tangent line is, what I'm going to do is use my protractor, the edge of my protractor, to represent what a tangent line would look like at different places on the graph. And I'm going to do what's called surfing the curve. So here, I would say at this place right here, the edge of the protractor is representing what the tangent line would look like there. And then let's say I'm talking about this place right here where x is 0. I'd say that maybe the tangent line would look something like this. So a tangent line is a line graph that connects with the given function at a certain value, but it does not connect in a neighborhood of values around that number. Okay, so like at A, I would say, so at x equals A, at this point right here, I would say maybe the tangent line would look something like that. Okay, so again, a tangent line, notice that this line does kind of come down and intersect over here, but it is tangent because it kind of represents the slope of the actual curve at that point. And it doesn't intersect in a small neighborhood around A. Okay? Okay, so that's what we're looking for, is a way to find the slope of a tangent line. But the funny thing is that think about the slope formula for a second from Algebra 1. You've known this thing forever. How many points do you need to find the slope of a line? And the answer is 2. You need to be able to figure out how much do you rise and how much do you run. And so here you won't have 2, you'll just have 1. You know, you just have this little point of tangency there. And so that's why we have a problem. So, so let's give you guys a warm-up. So let's see, so warm-up is to find the slope of the secant line. Oops. Now the word secant here is, a lot of people kind of worry like, oh no, trigonometry is going to be in this, and no, secant is a line that connects with your graph in 2 distinct places. Find the slope of the secant line. And so here's what we'll do. Think about this, my friends. If this is x equals a, then what are the coordinates of this point? If all we know is that this is some function rule called f, we don't really know what the rule is exactly. So what would the x coordinate be? It would be a. And then more of like, what would you do to get the y coordinate? And you would plug a into the function called f, so the y coordinate would be f of a. And then we're going to go down the number line a little bit, and I'm going to mark another x coordinate, and this is going to be called x. Kind of funny calling an x coordinate x, but here's the deal. A represents a constant, as in something that won't be moving, an arbitrary constant, but x is representing a variable, which is, in this case, it'll be something that will move. So let's think about what would the coordinates of this point be? So they would be x, the coordinate would be x, and then the y coordinate would be f of x. We're keeping this nice and generic, so it really wouldn't matter what kind of function we give you. You could just still, do everything the same way. And so the slope of the secant line, we're going to draw this in notation. I'm going to say slope. Remember, we used to use m for slope, and then a little subscript secant to represent the slope of the secant line. And so, in the secant line that I'm talking about is just a line that goes from the point A f of a to the point x f of x. Okay, so the slope of that line. So go ahead and figure that out. You could think rise over run, or you could do the formula y2 minus y1 over x2 minus x1, whatever works for you. Okay, so the slope of the secant line, if you were to just use the slope formula, you could do y2 minus y1, so that would be f of x minus f of a over x minus a. So rise, run. So you have this fun little expression that just represents the slope. Now, what we're going to try to do is figure out how can we kind of trick this slope formula into giving us, and I'm going to draw it in here, into giving us the slope of the tangent line. So at a f of a, I would say maybe the slope of the tangent line would be like something like that, maybe. So like this line here represents the slope of the tangent line at the point a f of a, that is. So what could we do? Well, one thing we could do, I mentioned that a is not going to move, but x could. So what we could do is we could scoot x a little closer to a. So like, let's say x wasn't way over here. Let's say x was like here. And then what if we did this exact formula between this point and the point a f of a? So if we did, we would end up with this line, slope of this line here. Whoops, it's not the color I meant. Slope of this line right here, which is not the slope of the tangent line, but it's closer to it. It's much better. So how could we get an even better, slope that would be closer to the slope of the pink line here? Well, maybe we could scoot x closer to a. Maybe some of you guys are kind of know where I'm going with this. How close would we need to scoot x to a to be able to use the slope formula and get the slope of the tangent line, that pink line right there? And the answer is infinitely close, like creeper close. Like, I don't know if you've ever been on a long car ride with a brother or sister or cousin or whoever, and you just get bored and you try to torture each other, and your parents have told you like to not touch each other because you've been hitting each other and bothering each other, and it's agitating the driver. And then inevitably, one person does, this to the other person, right? They're like not touching you, but they're getting infinitely close to touching you. And so that's how close we're talking here. X is going to get infinitely close to a. We can't have x be right on top of a, because if it was, f of x would equal f of a, and we'd have 0 over 0, and nobody knows what 0 divided by 0 is. And so we're going to have x get infinitely close to a. So if x was infinitely close to a, use your imagination. I know that's not infinitely close, so use your imagination. And then if we did the slope formula on it, then you'd end up with the slope of the tangent line. So the slope of the tangent line would be this exact formula, because it's still f of x minus f of a over x minus a, but we're gonna write something right in front of it. We're gonna write the limit as x approaches a. All right, my friends, and a little notation for you. This is the slope of a tangent line specifically where x is equal to this a value right here. And we have some fun notation for it that you'll want to get used to. So it's called f prime of a. And it means the slope of the tangent line to the graph of a given function f at the point where x is equal to a. And so worth memorizing, my friends, is that f prime of a is equal to the limit as x approaches a of just the slope formula, f of x minus f of a, so this is y2 minus y1, over x minus a, so this is x2 minus x1. Okay, it also has another name, and those of you that maybe have read ahead and looked into calculus, or you have a friend in calculus, this is known as the first derivative of f evaluated at x equals a, or also known as the derivative of f at x equals a. So this is also called I'm going to put the word first in there because if you just say derivative, it implies that it's the first derivative. The derivative of f at x equals a. Okay, all right, and you've got so many things that you could call this. So what we see here is conceptually what it means. This is its long name, and then it has a nickname. And so when you see this f with apostrophe of a, we never say apostrophe for that, even though that is what that looks like. But we would say it's f prime of a. All right, I'm going to put a big memorization cloud around what it is conceptually. And then its name and its nickname, and then the formula for it. Okay. A comment. I know that we are not in a classroom situation where I would hold you very accountable for being able to say these things carefully and sound all educated like. But I would like for you, whenever you write these things, to make yourself say the notation correctly. So you would say, and maybe go ahead and say it with me or after me, f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. So if when you're doing this, when you're in your head, instead of saying that, if you're saying horrible things like f apostrophe a equals lim x arrow a, you know, if you're not using the correct vocabulary in your head, or when you talk about this to other people in your class, whatever, you're really doing yourself a disservice. If you can say it correctly, you can do it correctly, in my opinion. Okay, so that's enough about that. I'm going to do kind of a fun little highlight on top of this because you should memorize this. And guess when you should memorize it? Yeah, right now. And guess when you get to forget it? Yep, as soon as your math career is over, whenever that is, okay? And maybe as soon as your kids are done with their math career too. No, just kidding. All right, anyway. Okay. All right, example 1. I remember I was in 3rd grade and I asked my mom for help with multiplying decimals. I didn't know what to do with the decimal and the answer. And she helped me and knew how to do it. And then she said, honey, I think this is the last thing I'm going to be able to help you with. Good luck. All right. Okay, so for part A, let's work on a really simple graph here. So let's do graph f of x equals x squared. I know we are all super comfortable with that one. So go ahead and do a quick 5-point of accuracy graph of that one. Try to make it, try to maybe take a little pride in it when you do that if you need to. Those of you with graph paper in your notebook, you're like probably pretty glad you have graph paper. All right, my friends, let's graph this and try to make this look pretty good. So 0, 0, plus or minus 1 goes up to 1, plus or minus 2 goes up to 4. Okay, so so nice little parabolic graph here. Okay, now for part B, I'm gonna have you do this, kind of attack this from a couple different angles, okay? So, so the first thing I'm gonna ask you to do is to, let's say, estimate or approximate each derivative, okay? So this is where you are seriously just going to eyeball it, okay? And this is an important part, so so make sure you don't skip this type of thinking here. Okay, so let's say, so this is the graph of f, right? And so let's say I ask you, what do you think f prime of 0 is? I'm just gonna butt out for a couple beats and let you think about that. Okay, so now let's think about, what does f prime of 0 even mean? So f prime of a means the slope of the tangent line to the graph of f at the point where x equals a, and here your a value is 0. So in this case, it would mean that if you were to kind of surf the curve with a tangent line, you're supposed to stop where x equals 0 and figure out what the slope of the tangent line would be. And so if you were thinking the answer is 0 or something like that, then you had a pretty good approximation there. Okay. Leave, let's see, let's have you leave like maybe 3 lines of space, 3 or 4 lines of space. And then let's talk about what would like f prime of 1 be. And you're just estimating it. So like if you don't feel comfortable, I feel like that one we should feel pretty comfortable saying 0, but you could always say it's maybe about 0 or something like that. So for f prime of 1, you might feel like you're approximating a little bit more. So really what I'm trying to do here is make sure you understand conceptually what does the first derivative give you and from a picture. It's very important that you can do that. Okay, so f prime of 1 would mean the slope of the tangent line when x is 1. And so if you were surfing the curve, you would pause your surfing adventure where you have a tangent line at x equals 1. And so I'll go ahead and maybe I should be drawing these in. I'll use some highlighter here. So the first one, f prime of 0 was this, the slope of that line. And then f prime of 1 would be about, can I use a straight edge? So f prime of 1 would be the slope of maybe that line right there. And so think about, what do you think the slope of that line is? So I'd say maybe something around, I don't know, my graph makes it look like it could be like about 3/4 or sorry, 1 3/4 or 2, something like that. So let's say about 2. And then let's kind of, and then this is going to get a little harder, but like let's say I asked you what is, let's go over here, f prime of 2. Actually, you know what, let's do some negatives. F prime of -2. Not that it's that much harder. Okay, f prime of -2. So that would be where the slope of your tangent line, or we'd be finding the slope of your tangent line over here at -2. So that would be like this guy. And so, you know, what would the slope of that be? Notice it's negative this time. So let's see, I went down 1, 2, 3, 4 and over 1. So it looks like maybe it's about -4. Okay. Let's have you approximate one more, f prime of 1/2. So that's here. So that would be like the slope of this line right here. Oh. Doop, boop. Whoop, I missed. There we go, slope of that line right there. So I would say something about one or so would do it. Okay, so this is just an exercise in seeing, do you understand, graphically speaking, what f prime of a number is? And so hopefully these answers or ballpark answers make a little sense to you. So now let's talk about, what if I did not say estimate? What if I said evaluate? Then all of a sudden this formula right here would be necessary. So we thought f prime of 0 was 0. We were right. Now we'll just show how to actually find it. So you would need to have this memorized, and this is a good time to pause the video and try to memorize it so that you can do this problem from memory and then check in with me and see if we get the same thing. So f prime of 0, you're just going to replace all the a's with zeros. So it would equal the limit as x approaches, a is a 0, of f of x minus f of 0 over x minus 0. Now we're going to specialize the fact that f of x is x squared. And so this would equal the limit as x approaches 0 of f of x, you can replace with x squared, minus f of 0, which would be 0 squared, or 0, over x minus 0. So I'm just going to rewrite this as x squared over x. Okay? Well, if I was to let x go to 0 right now, I'd get an indeterminate form, but luckily you can see the x's cancel, so we'd be left with the limit as x approaches 0 of x. And now do direct substitution, and so let x approach the value of 0, and you get 0. And my spacing is not the greatest. Okay, you get 0. Okay. Notation, I'm going to be picky about it because when you, a year from now, when you take the Calc BC exam or Calc AB exam, whatever you're taking, someone who does not know you or know anything about you is going to need to read your work, okay? So here's what I'm looking for, my friends. Equal signs lined up. You do not have to write f prime of 0 each time. You write it to prompt what you're finding, and then you bring it down to match your final answer, and you box your answer. The limit statement is written until you finally let x attain the value of 0 and you get your final answer, okay? All right, my friends, so now f prime of 1. We thought that it was about 2. Let's check and see what it is. So we're going to go ahead and use this definition. This time your a value is 1. So this would be the limit as x approaches 1. I'm going to skip the step where I write f of x minus f of 1 over x minus 1. And I'm going to replace f of x with x squared. F of 1 would be 1 squared, or 1 over x minus 1. If you do direct substitution, you can see you'd get 0 over 0, so we're going to use the factor and cancel technique. So we're going to have the limit as x approaches 1. We're going to factor this difference of 2 squares, like so. And then with or without sound effects, you cancel out this factor, this common factor. And then you can let x go to 1 on the remaining piece. I'm just going to skip a step and go ahead and let that last x attain the value of 1, and you get 2. And it turns out the slope of the tangent line at 1 is not just approximately 2, it is exactly 2. Okay, f prime of -2, we're going to find out it's exactly -4. By using this definition here, just your a value is a -2. So we'll have the limit as x approaches -2 of f of x, which in this case is x squared, minus f of -2, which would be -2, the quantity of -2 squared, which would be 4 all over x minus negative 2, which would be x plus 2. We're going to end up factoring and canceling the top factors as x plus 2 times x minus 2. The x plus 2's cancel. Let the remaining x attain a value of negative 2, and you'll get negative 4. So the slope of the tangent line is exactly negative 4. Okay, so here's what we're looking for. Can you understand what this formula gives you conceptually? That's the slope of the tangent line at a given x value. Can you use the formula to evaluate a derivative at a given point? And then can you use the correct vocab when you do it? Okay, last one, we thought f prime of 1/2 was about 1. We're going to find out it's exactly 1. So this would equal the limit as x approaches, what number? 1/2, good. F of x is x squared minus f of 1/2 would be 1/4 all over x minus your a value, which is 1/2. Simplifying this, we're going to use factor and cancel again. The limit is x approaches 1/2 of x plus 1/2 times x minus 1/2 all over x minus 1/2. Bye-bye indeterminate form. Let your remaining x approach your target number. You'll have 1/2 plus 1/2, which is 1. Bring your prompt down. And we have the f prime of 1/2 is exactly equal to 1. All right, my friends, I hope you are starting to feel comfortable with using this definition of derivative. If you don't have it memorized yet, take a minute and memorize it and see if you can do the next problem with it from memory. Example 2. Okay, we're going to break this into 2 parts. Part A, find the slope of the tangent line to the graph of f of x equals square root x at the point 9, 3. Okay, good time. You pause the video, see if you can do this, okay? We're getting close to the end of the lesson, so you're gonna wanna make sure that you can do this kind of thing on your own. Okay, so first, what's the notation that we should use that would mean the slope of the tangent line to this graph at the point 9, 3? So what we're trying to find here is f prime, so that means the slope of the tangent line to the graph of f, but at what number should I put in there? It's always going to be the x coordinate, so it would be 9. So we're trying to find f prime of 9, okay? And that would equal the limit as x approaches, and what's your a value? It's 9, good, of f of x is the square root of x this time, minus f of 9. You could plug 9 in, or you could notice that they told you what the number is. It's 3 over x minus, and your a value again is 9. Okay, from here you could use the conjugate move on the numerator if you want. It would totally work. Another way to do this would be to treat the bottom like a difference of 2 squares. X is the square root of x squared, and 9 is 3 squared, and you could still use the factor and cancel technique. So bottom is a difference of 2 squares. It's equal to root x plus 3 times root x minus 3. So square root x minus 3 could cancel out. You're left with, I'm going to put a 1 there just to show, and then I'm going to skip this little step here that I was about to show. So let's let x approach 9 and see if we got away with it. On the top we'd have 1. On the bottom we'd have the square root of 9 plus 3. So we'd end up with square root of 9 is 3, so you'd end up with 1/6. There we go. Okay. Part B. Find the equation of the tangent line to F at the point 9, 3. All right, my friends, so go ahead and think about that. Okay, so something that I'm going to be doing in the future is I'll kind of ask you sometimes to graph what just happened. And so what I'm going to do here is I'm going to graph what's happening in the first place, just to make sure that we can see how very easy this is going to be and why it's so easy. So when I ask you to graph what happened, it's very not technical terms there, then what you'd graph is the original function So let's graph square root x. So square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, etc. So here's f. And then in part A, you found the slope of the tangent line to this graph at the point 9, 3. So you were finding the slope of this line. And you found that the slope is 1/6. And I hope that's believable that you could have a rise of 1 and a run of 6, that it's that shallow of a line. I'm actually going to use kind of rise over run, so down 1 to the left 6 type thing to draw that in. Did I just do that funny? No, down 1. Wait, down 1 to the left 6. Yes, yes, rise over run. Okay, yes, that looks funny. That looks weird. I'm not doing that. Okay. There we go. Okay, so something like that. I feel like I did something really weird there. I'm not sure what. Anyway, I'm not going to try to worry about it. Okay, so here's the equation of the, here's the line that you found the slope of here. Yeah, so up 1 over 6 or down 1 to the left 6. Yeah, I don't know. Okay. Anyway, whatever. Okay, so what would the equation of that line be? Well, you know the slope and you know a point, you know the point of tangency, so you could just use point slope, no big deal. So y minus 3 equals your slope times the quantity x minus 9, and then we're done. There we go. And I encourage / invite you to leave your answers in point slope form. I know that some students from kind of being tortured probably, I'm guessing in Algebra 1, with having to always put this in y equals mx plus b form, they kind of learn to not like it. But in calculus, we just leave things in point slope form. We don't bother simplifying it. So hopefully that'll help you start liking it, because from here on out, this is kind of where we live. Y equals mx plus b kind of takes a back seat from here on out.